Before we get into our next probability distribution, we need to discuss two forms of sampling: sampling with replacement and sampling without replacement. Both kinds of sampling are readily described using the simple example of choosing marbles from a bag. If we choose a marble from a bag and then put it back before choosing again, that is called sampling with replacement. When this occurs, the probability of choosing a certain kind of marble from a bag is the same every time, because we are choosing from exactly the same set of marbles. That is, the sample space is always the same. Another way of looking at it is, the outcome of each experiment, and by experiment I mean choosing a marble, is independent of the outcomes of previous experiments, and the probability of each outcome, such as choosing a certain color of marble, is known. So if we label one type of marble as a success and all others as failure, then effectively each choice of a marble is a Bernoulli trial, and the possible outcomes of choosing n marbles in this manner follows a binomial distribution. On the other hand, in sampling without replacement, a marble is not put back in the bag after it is chosen. Therefore, regardless of the kind of marble it is, because it is removed from the sample space, the probability of choosing any kind of marble next time is different. Here we see how if we have a bag of 20 marbles, and there's a 40% chance of choosing a white one the first time, and 60% of choosing black, then the probabilities have changed for the second marble regardless of the color of the first marble. In other words, each trial in a sequence of n is not independent of the other trials. Therefore, we cannot use the binomial distribution to describe the probabilities of all possible outcomes. Instead, we use what is called the hypergeometric distribution. It is useful when it is known that a certain number of outcomes in a large set are successes and the rest are failures. We still perform n experiments or trials in which the outcomes are taken from this large set of successes and failures without replacement. We then want to know what is the probability of k successes in these n trials, where k is any integer between 0 and n. These probabilities follow the hypergeometric distribution. What would be an example of dependent trials that would call for the hypergeometric distribution instead of a binomial distribution? Consider the task of taking n light bulbs from a set, and it is known that a certain number of light bulbs within that set are defective. What is the probability of k light bulbs out of the n being defective? If we start taking light bulbs and they turn out to be working, then the probability of choosing a defective light bulb is increasing, because the number of defective light bulbs is not changing while the total number of light bulbs is decreasing. It follows that the probability that the next light bulb is not defective is decreasing. We can use counting principles to compute the probability of k successes out of the n trials. The idea is to determine the number of ways to choose k items from a set of capital N successes, and the number of ways to choose n minus k items from a set of capital M failures. Each of these is given by a binomial coefficient, and because we're choosing k successes and choosing n minus k failures, we multiply these to get the total number of ways to choose k successes out of the n. Then we just divide by the total number of ways to choose n items out of the entire set of capital N plus capital M, and at last we have our probability. Now, what are the mean and variance of this hypergeometric distribution? It turns out that the mean, or expected value, is the same as for the binomial distribution, n times p. The variance is different. Note that it is equal to the variance of a binomial distribution, n times p times 1 minus p, times this additional factor. However, it is worth noting that as the number of total items from our set of successes and failures, capital N plus capital M, goes to infinity, and in such a way that the proportion of successes, or p, remains the same, then this term goes away, and the variance converges to that of a binomial distribution. This makes sense based on intuition, as the distinction between sampling with replacement and sampling without replacement goes away when we are choosing from a set of infinitely many items. Let's return to our example involving light bulbs. If 10 out of the 100 are defective, and we choose any 20 of them, what is the probability that at most 2 light bulbs will be defective? This is the same as the probability that either 18, 19, or 20 light bulbs are working. Because each of these 3 outcomes are mutually exclusive of the others, we can simply compute these probabilities using a formula from a previous slide, and then add them up. We find that the probability of at most 2 defective light bulbs is rather high, because 90% of the light bulbs are working. We now turn to our next distribution, the Poisson distribution. This distribution applies to what is called a Poisson process, which is an experiment that counts the number of successes not out of a fixed number of trials, like in the binomial and hypergeometric distributions, but out of some other quantity, such as a period of time or an area, or whatever quantity that serves as an appropriate domain. Whatever domain we use, key characteristics of a Poisson process are that, number 1, the average number of occurrences, that is, successes or failures, within any subdomain is equal to that of any other subdomain of the same size. And number 2, the number of occurrences within any subdomain is independent of that in any other subdomain. Here are some examples of Poisson processes that happen to use time as the domain. In the first one, we are interested in the probability of a certain number of accidents occurring in the given area over any given period of time, given the average number of accidents within a particular amount of time, say accidents per hour. Similarly, in these other examples, we are interested in the probability of a certain number of web requests per unit of time, the numbers of recalls received per unit of time, or how many customers are served per unit of time. But other domains can be used as well. For example, consider the process of manufacturing sheet metal. We might be interested in the probability of a certain number of square feet having defects, so in this case, area is used instead of time. The Poisson distribution is defined in terms of a mean number of successes, whatever success means in the given context. Given this mean mu, the probability mass function for the Poisson distribution is given by this formula here. Note that unlike the binomial and hypergeometric distribution, the domain of a Poisson distribution is infinite, as there could be any number of successes, since there is no upper bound on the number of experiments. Also, we note that the variance of a Poisson distribution is equal to the mean. Here we see various Poisson distributions for different choices of mu. We note that it's not symmetric, though it does become more symmetric as the mean increases. As an example, suppose that an average of 0.5 defective tires are produced per hour. That means the number of defective tires per hour follows the Poisson distribution with a mean of 0.5. To obtain the probability of k defective tires being produced within the next hour, we can simply substitute k into the probability mass function, as is done here. Now, what about the number of defective tires produced during an 8-hour workday? Because the average number of successes is the same for any two intervals of the same size, we can simply scale the given mean of 0.5 defective tires per hour to a whole day. So the average number of defective tires during an 8-hour workday is 8 times 0.5, which equals 4. Then, we can use a probability mass function to determine the probability of producing at most 3 defective tires per day, which is the same as the sum of the probabilities of producing 0, 1, 2, or 3 defective tires. We've seen that the graphs of the probability mass functions for both a binomial and Poisson distributions have peaks at their expected values. Because of this, we can actually use the Poisson distribution to approximate the binomial distribution. This is convenient because the probability mass function for the Poisson distribution has a simpler form than that of the binomial distribution, which facilitates analysis. All we have to do is use the mean of a binomial distribution, n times p, in place of mu, the mean of a Poisson distribution. However, we have to be careful. This approximation is only valid if the number of trials is high enough, say at least 20, and if the probability of success of a Bernoulli trial is quite small. The importance of these conditions can be seen here. In the left plot, we have n equals 15 and p equals 0.1, which does not satisfy the conditions given on the previous slide, and we can see that the probability mass functions don't agree very well. However, in the right plot, we have n equals 20 and p equals 0.05, and we get a much better fit.